CHE241 example 5. So before that I change it to black for the pen. Okay, example 5, chapter 8.1 Hagen-Posela. So in this example I will show you how you will apply the Hagen-Posela equation for the case of lamina and a straight pipe problems. Okay, this is the question. A liquid with specific gravity and dynamic viscosity of 0.789 and 1.19 times 10 to the power of minus 3 kilogram per meter second, respectively, flows through a 0.5 meter diameter pipe. In order to maintain the type of flow for a volume flow rate 1.129 times 10 to the power of minus 3, a certain value of pressure drop should be maintained along 3 meter pipe length. Calculate the suitable pressure drop. So from here, we cannot directly assume that these types of equation can problems can directly use Hagen-Posela. So we know that this is a straight pipe because 3 meter pipe length, straight pipe with 3 meter length. Now what we have to do is we have to calculate what is the Reynolds number. So first you have to calculate what is the Reynolds number. We know that the Reynolds number equation is rho v d over mu. So I know that in these problems, it states that the dynamic viscosity of the liquid is 1.19 times 10 to the power of minus 3. If the question gives you kinematic viscosity, it is suitable for you to use the kinematic equation, okay? Reynolds number with kinematic viscosity equation. But now I will use Reynolds number rho Vd over mu. But it is okay if you use these kinds of equation, but before you substitute the value into this equation, you have to convert kinematic viscosity to dynamic viscosity. Okay, if in the question gives you kinematic viscosity. Now the question gives you dynamic viscosity, therefore I will use Reynolds number rho Vd over mu. Now we take a look at the one by one terms inside this Reynolds number equation. So rho, do we have rho? So the question gives us specific gravity, therefore we have to change specific gravity to the density. So we know that the specific gravity equation is rho of the substance divided by rho of water at 4 degrees Celsius. So this will be 1000 kilogram per meter cubic. So rho substance is equal to Sg specific gravity times with rho water at 4 degrees Celsius. Now this is rho liquid. So we do have the Sg for the liquid, which is 0.789 times with 1000. We will get that the value of the density for the liquid is 789 kilogram per meter cubic. So we already solved for density. Now we take a look at the velocity. V here is a velocity. So do we have any velocity statements in this question? No. So where do we get the velocity values? So from here we know that the question gives us the volumetric flow rate or volume flow rate, which is 1.129 times 10 to the power of minus 3. Therefore, what we have to do is we have to calculate velocity from the volumetric flow rate. So to find the velocity from the volumetric flow rate, we know that the volumetric flow rate equation is equal to U times with the area. Okay? So rearrange this equation. U is equal to Q over A. Now we have to calculate what is the area. So area here is pi d squared over 4. So pi, the diameter is 0.5 square over 4. Okay, so you will get the area of your pipe is 0.1963 meter square. So this is the area. And then what about the volumetric flow rate? In this question already give us in terms of meter cube per second. So if the question gives us in liter per second, we have to change it into SI unit, which is M3 meter cube per second. Now directly substitute your value of Q and A into this equation. Okay, 1.129 times 10 to the power of minus 3 meter cube per second divide with 0.1963 meter square. So you will get the value of velocity is 0.00575 meter per second. Okay. Next, what we have to do is we will directly substitute all this information into Reynolds number because Reynolds number equation, because diameter and dynamic viscosity is already been given in your question. So your Reynolds number equal to 789 times with 0.00575 times with 0.5 divided by 1.19 times 10 to the power of minus 3. So after that, we will get the Reynolds number for this question is 1906.197, which is less than 2400. And then this flow is laminar. So now we know that this flow is laminar and a straight pipe. Therefore, we can apply Hagen-Poiseuille equation. So apply Hagen-Poiseuille equation to find what is delta P. So I will use delta P 128 mu QL over pi d to the power of 4. So I will substitute all the value. So mu is 1.19 times 10 to the power of minus 3 times is 1.129 minus 3, and then length is 3 meter, already states in the question. Okay, divide by pi 0.4 to the power of 4. So from here you will get your delta P value is 0.00262.7 Newton per meter square. So this is your value of the pressure difference for this question. So you have to calculate what is the suitable pressure drop. Okay, so that's all for